Hi, I'm Jason Cottrell, founder and CEO of RCAM Technologies. Today I'll be presenting our National Offshore Wind R&D Symposium presentation on a low-cost modular concrete support structure and heavy lift vessel alternative. Before we start, just a little bit about RCAM. We presently have 5 employees. We are a growing startup with offices in California and Colorado. We're expanding somewhat rapidly at about a rate of about 2 employees per year. Although small, we have the benefit of working with an international network of R&D partners. For this project, the primary partners that we're working with are illustrated here. It's a multidisciplinary team, primarily US-based, supplemented with select European expertise in offshore wind. Just a bit about these partners. So WSP USA is performing the design of the concrete structure. University of Nebraska-Lincoln is performing the analysis of the manufacturing and assembly process. Metzco is a marine architect. NREL is well known. They're helping us with LCOE modeling. Cathy is a UK and US-based geotechnical engineering services firm. RR&D Engineering is a small company providing load analysis for the project. Structural Technologies, University of Delaware, and Tufts University are providing consulting and advisory support. In Structural's case, it's on the post-tensioning of structures and heavy lift equipment and needs. University of Delaware providing expertise on their previous study industrializing offshore wind, upon which we're building on their shoulders, and Tufts providing concrete design expertise. So these are 5 of the 7 wind turbines presently installed in the US. The East Coast states are targeting to install approximately 2,000 of these wind turbines in the next 10 years. The average cost is about $10 million, resulting in a $20 billion offshore wind foundation market. However, there's a number of challenges. These are the 3 primary challenges that our technology addresses. The first being that the East Coast lacks a sufficient heavy steel fabrication supply chain necessary to manufacture the jackets shown in the previous slide. There are no Jones Act compliant installation vessels presently available in the US or that can install a next generation turbine in the world at this point, to my understanding. And of course, the right whale is an endangered species which inhabits some of the areas of the targeted installation areas. So our solution is illustrated here on the right-hand side. We plan to use modular concrete technologies to manufacture everything in gray here. The design is such that it's self-floating and can be wet-towed to the site and installed without a heavy lift installation vessel. Here's a brief overview of the project. The primary goal of the project is to prove the feasibility and advance the design of the low-cost modular concrete suction pile support structure and heavy lift vessel alternative. The technology uses a suction bucket assembly, as shown here on the right-hand side, which is basically an upturned bucket, which is a foundation that can be installed effectively noiselessly into the seafloor. It's a 2-phase study. We've just completed phase 1, which was a $300,000 effort with plan for 9-month duration that focused on the conceptual design of this technology and feasibility of this technology, as well as several concept variants. In phase 2, we'll be continuing to explore some concept variants identified in phase 1 and advance those concepts to preliminary design stage, as well as perform a number of commercialization and stakeholder outreach activities. So just briefly about the phase 1 results and key findings. Phase 1 has 10 subtasks. 10 deliverable reports were completed, resulting in about 220 pages of materials. It was performed on an accelerated 7-month schedule, and we recently received a phase 2 decision to proceed to phase 2, which we began last month. One of the key findings is that the concept is feasible. All modular concrete designs that we considered were concluded to be technically feasible, and I have more information about cost in the following slides. We varied the number of legs, explored a telescoping tower option, considered several different diameters, and settled on what we believe is a reasonably optimized 45 meter radius, leg radius, and that result was a nearly 12,000 metric ton design. In addition, we found that the concept does indeed provide a heavy lift vessel alternative. The turbine can be installed fully assembled or partially assembled, or in a more traditional fashion, similar to a monopile or jacket substructure. We looked at 3 different transportation and installation concepts. We concluded that for our purposes, a telescoping tower is not required, although it offers some benefits if you need to wet tow your assembly underneath a bridge. We also identified that at the installation phase, as illustrated here, identifies the most risk. Here's some more detail on one of the concepts, in which we take what we call a suction bucket assembly, which has 3 suction buckets connected by a frame, pre-install that assembly at the site, and then bring out the turbine connected to an auxiliary flotation system, in this case a Jones Act compliant barge, which is connected to the turbine, and then use basically tension members to pull the foundation down to the suction bucket assembly, thereby helping to address one of the primary risks. University of Nebraska explored 2 different manufacturing and assembly methods. One of their primary conclusions is that the production rate target of 1 foundation week is achievable with 3 lines. What's illustrated here is one method of using a match cast type system, and the method that they envision of lowering the foundation into the water. This is another structure that was performed, and we would be using comparable technologies to lower the structure into the water. A third key finding is that automated manufacturing offers significant cost reduction opportunities. There's a wide range of automated manufacturing, one of which RCAM Technologies has been focusing on is 3D concrete printing. And what's illustrated here is our RCAM team at the time with a containerized robot system that we can use for 3D concrete printing research purposes. One of the key questions, of course, in metrics is what sort of costs can you achieve? The costs are summarized here, as well as cost targets for 3D concrete printing. We compared the NREL 15 megawatt foundation on a monopile foundation type in 50 meters of water. This number here represents the capital cost for that foundation. We compared that to the tripod foundation solution, which is slightly more capital cost. However, there's some savings in avoidance of a wet wind turbine installation vessel, which effectively results in about the same levelized cost of energy at the end of the day. And we were quite pleased with that, considering the fact that we have not yet had the opportunity to optimize the foundation and pursue the identified cost out paths. On the next column here is RCAM's estimate of the savings that for a 3D concrete printed foundation. You can see that the primary savings comes from the material cost. The labor cost. Some costs are expected to go up, such as the material cost due to the concrete materials being somewhat more expensive than traditional cast materials. But overall, we're anticipating something like a 40% manufacturing cost reduction, which would result in something like a 1.5% LCOE reduction. One of the cost reduction opportunities not reflected here is, of course, the ability to scale up the turbine size to 20 megawatts or larger, which is one of the most effective ways to reduce the levelized cost of energy. I'd like to provide just a few words about the state-of-the-art of 3D concrete printing and our motivations for exploring that technology in phase 2. What's shown here on the left-hand side is a containerized printing system. I don't have time for the video, but you can go to Black Buffalo's site and probably find this. Black Buffalo is a startup backed by Hyundai 3D Concrete Printing Systems. Black Buffalo is located in New York. What's shown on the upper right-hand corner is a gantry-style system, and one of what GE announced is a prototype, probably a subscale prototype of an onshore wind turbine tower base that has been 3D concrete printed in Europe. What's shown in the lower right-hand corner is a radial arm printer. This one by a company that was originally started in Russia is now in the US. And what's interesting about this photo is that the size of the component being manufactured here is of comparable size to the suction bucket foundation that we plan to print, or the suction buckets for that foundation and the suction bucket anchor. This project also has the benefit of leveraging extensive prior and related ongoing work. As illustrated here in 2016, the technology vision, I would say, began while I was working at the National Renewable Energy Laboratories. There's some prior work not reflected here in 2012 by Henrik Stiesdal of Siemens previously, and Barak Koshnevitz from the University of Southern California, who's widely considered one of the main inventors of these technologies. In 2017, we received the first ever public funding for 3D concrete towers made possible by the California Energy Commission. In that project, we will be manufacturing and are testing concrete cylinders of various sizes that are post-tension, both in static and fatigue. More recently, the first ever application of 3D concrete printing to offshore wind was enabled by U.S. Department of Energy, SBIR, followed by National Offshore Wind R&D Consortium grant, which allowed us to take that first ever conceptual analysis to the next level with industrial partners. More recently, we're performing some work on 3D concrete printed anchors and also working to continuing to develop this mobile 3D CP system or containerized system using a State of Colorado grant, some California Energy Commission grants, as well as some funding by the Floating Wind Technology Accelerator Competition for developing and assessing these 3D concrete printed anchors. So these projects we've consolidated into this slide that we call our vision slide that helps visualize what these assemblies and how these different components might be all manufactured on one port. So what you see here is 6 different printers as shown in red. This is one printing concept. The wind turbines are arranged in rows, or the foundations are arranged in rows, and the printer basically goes from one foundation to the next, printing the foundation, thereby allowing the foundation to cure and minimizing handling costs of those relatively large and heavy foundations. What's shown in the middle here are suction bucket assemblies that can also be printed on site, suction buckets illustrated being printed by this printer, as well as suction bucket anchors which could be printed for a floating wind turbine system. Other components such as civil infrastructure or energy storage concepts, which we have begun to explore, could also be printed at a site like this and wet towed to the site, minimizing the vessel needs. So as part of this study, we brought this home, so to speak, by starting to analyze a port in New York. So New York has a port study in which we plugged our technology into, so to speak. And we looked at several different ports that they identified as good candidates for supporting offshore wind. We found the Brooklyn Marine Commerce Terminal just shy of the Statue of Liberty. It's an underutilized port here presently in New York. So using some drawings provided by the New York, we basically took this port drawing, plan drawing, and drew in 0.5 gigawatt of the suction bucket assemblies that could be manufactured on this site. So this represents about $50 million annually of potential throughput for these suction bucket assemblies. What's illustrated here is the possibility of also using the same site to manufacture anchors for floating wind turbines that reduce the cost by on the order of half to maybe up to 80%. What's interesting about these ports, in addition to being relatively underutilized and providing jobs and economic developments for the nearby communities, but they also are usually near some sort of concrete facility. In this case, there's a Lafarge cement batch plant half a mile away that can be accessed either by truck or by barge to provide the materials to the site. So looking forward to phase 2, we've just begun that last month. It's again a 14-month study. We have 3 primary subtasks or technical subtasks, and the objective of that study is to continue development and assessment of some of the concepts developed and analyzed in phase 1. Task 5 is one of the main tasks. We are going to identify additional northeastern reference sites for manufacturing, assembly, and installation. Task 6 is a relatively big task in which we're going to further design and advance the concepts. You can see and read for yourself these different subtasks here. In Task 7, we're going to plan the follow-on structural testing, field demonstration, and perform some certification activities for the selected design. Task 8 is a stakeholder advisory panel comprehensive workshop. If you have interest in attending that workshop, which is an invite-only workshop, but they tend to be relatively large, please contact me. Or if you have any other additional questions, please contact me. Here's my email address. Thank you for your time. I hope you enjoy the symposium.